Okay, so here's a little computer output that's listed in question 59. And for going over it, I'm less concerned really about the context of the question, although it tells me the X and Y right there. The first rule of computer output is don't wig out. So there's a bunch of stuff on here that the computer software will give us that we haven't learned how to use yet. First of all, this stuff right here is spring semester stuff. We haven't done it yet. We don't need it yet. So you think, well, why did they put it on there? Well, they put it on there because that's what the program does. This is a program called Minitab. It gives you output like that. It's just like when you look on your calculator and it tells you stuff you don't use or don't understand yet, you ignore it. Likewise, we haven't talked about any adjusting of r squared, so don't worry about it. At one point I looked it up to see what it meant. I don't use it very often. I forgot. It doesn't matter. Don't worry about it. This, on the other hand, we should be able to understand. That's r squared. We usually write it like this, and sometimes we'll write it like 0.746 instead of 74.6%. Likewise, this number next to it is the standard deviation of the residuals. This is the one that's the square root of 1 over n minus 2 times the sum of the residuals squared. This tells me the typical amount that I'm wrong. So for example, here at 7.76, this means when I use the linear regression equation to predict percent return based on breeding pairs, I'm usually 7.76 off. That's typically how wrong I am. So if this number was smaller, the numbers would be closer to the line. For example, here I have a bigger S than I have here, assuming the scales are the same, because these points are closer to the line. So the standard deviation of the residuals, or the spread of the residuals, or the spread of the measures of wrongness are smaller over here than they are here. R and r squared are kind of cousins to S. They measure similar things, how spread out the points are. I guess also we don't use this yet. We'll use this in the spring semester. So we're starting to really reduce what we have on here to use. So we're left with a constant and a breeding pairs, and both of these things have cofs, whatever that is. So I'm going to use these two numbers somehow to make an equation. The cof of the constant, that's the coefficient of the constant. We usually call this number right here the y-intercept. The coefficient of breeding pairs is the coefficient of the variables. This number right here we call the slope. So now my equation then is going to be y hat equals 266.07 minus 6.650x, where x is the breeding pairs and y is the percent return. And then the questions go through in this particular problem asking you to interpret S, which I just did, asking you to, I think, use this equation to make a prediction. Okay, we should be able to handle that. We talk about finding R. How are we going to find R from this? Well, you square root r squared, but we also have to worry about if it's positive or negative. So how do you know? Look at the slope. The slope is negative. R is going to be negative. So take the square root of 0.746 and make it negative. And then they ask you this somewhat cryptic question. What percent of the year-to-year variation in percent of returning males is accounted for by the straight line relationship with number of breeding pairs the previous year? That's a thesaurus type method of asking what percent of the change in y is explained by the least squared regression line of y on x. That is r squared put in context of the question. So that particular question, once you recognize that, is very easy. It's 0.746 or 74.6%. If you don't recognize that, you're probably doing all sorts of calculations that would be unnecessary and most likely incorrect. So there's computer output, not hard to go through or understand, especially when you start eliminating stuff that you don't know. Just eliminate it.